Have you ever thought, this is a strange coincidence? Like receiving a phone call from someone you were thinking of. Or like meeting someone in an unexpected context. Or finding what looks like a secret message in your dog's bowl. But you are a scientist and you do not believe in coincidences, do you? So let's model this.
Release!
Well, let's null model this.
Jarvis, you up?
For you, sir, always.
I'd like to open a new project file, index as Mark II.
So how do we figure out if our dog truly wanted to tell us something? Besides asking her, we can approach the issue from a statistical perspective. The problem reduces to quantifying the odds that the shape designed by the keyboards in the bowl has naturally emerged without our best friend's intention to tell us something. One possible solution consists of replicating multiple times the experiment of shaking the bowl and then checking if the keyboards have designed something close to the mysterious hair shape under investigation. Some standardization in the experiment might be helpful to justify our doctoral degree. And generating 10,000 random bowls seems like a good compromise to get some robust results. We can then use a frequentist approach and count the number of times the keyboard pattern in a random bowl depicted a hair shape. Such a number, quoted by the number of random bowls, gives us the sought after p-value. She significantly loves us. This example shows precisely what Null Model Analysis is all about. Ecologists often measure patterns in natural systems and then synthesize them with metrics and indexes. Now, if there is no scope beyond the measure itself, one could be satisfied with raw numbers, such as when quantifying biodiversity in terms of number of species per locality. However, it is often the case that one wants to link the observed patterns to a set of specific ecological processes. There, it is essential to build a frame of reference to discriminate between the relative contribution of these specific processes to the target pattern and that of non-relevant, potentially confounding factors. One common approach to the issue is generating a large set of randomized versions of the system and then comparing the pattern measured in the real-world dataset with the patterns measured in the randomized versions, as we did in the dog bowl experiment. Although this seems an intuitive and straightforward solution, there are many aspects to consider. We can summarize them in the general question: how do we create the simulated or null set for comparison? To be more precise, which features of the starting system we should randomize and which ones we should preserve in the simulated set? This choice can dramatically affect the results of the analysis. Let's consider the example of the non-random arrangement of keyboards in the dog bowl. There, it was intuitive that, to be fair, we had to perform the randomizations in a bowl identical to the starting one. Also, we had to use the same number of keyboards and possibly keyboards of the same kind. Not satisfying those criteria using a very different bowl, or a much larger or much smaller number of keyboards, or keyboards of another brand, would have been a bit like cheating. That is, it might have generated a situation with an artifactually low or high probability of obtaining a keyboard arrangement similar to that observed in the initial bowl. However, even controlling for the ball shape and size and the number and quality of keyballs could not be enough for a truly unbiased experiment. It is reasonable to assume that the hair-shaped pattern has emerged in the ball due to our dog eating away keyballs, not from shaking the ball. To account for that, we might replace our randomization procedure based on shaking the ball with a new one, where we start with a full ball and then we remove keyballs at random until the number of keyballs matches that found in the original ball. We might go further and obtain a heat map of the dog's preference for different ball sections through observation of the dog behavior under standard conditions. We might then adjust our removal strategy based on the heat map by selecting the keyballs to be taken out of the balls with a probability proportional to the dog's preferences. These attempts would drive us closer to an ideal situation where our null model is reproducing all the potential processes that eventually led to the emergence of the hair-shaped patterns, with the only exception of the dog's will. If after all this effort to reproduce precisely the conditions where the hair shape emerged, still the pattern does not show up in our simulations, we should consider ourselves sure that the dog truly loves us. The more constraints we implement in the randomization procedure, the more we will restrict the set of potential outcomes. If we do not constrain the amount of food or the ball shape and size, the number of keyball arrangements is very vast. But the number progressively shrinks as we keep on adding constraints. This has fundamental consequences for our ability to detect a target pattern. Let's assume that the hair-shaped pattern is always one possible configuration, regardless of how many constraints we impose, and that each possible configuration has the same probability of being randomly generated. In such a situation, we could artifactually drive the p-value by acting on the constraints alone. By adding constraints, we might reduce the number of possible keyball configurations and increase the probability of obtaining the hair-shaped pattern so much as to start doubting about our dog's love. From the opposite perspective, by reducing the constraints, we would be most likely reassured that our dog loves us, even if she did not intend to leave a message in the bowl. To define this issue in statistical terms, by relaxing constraints too much, one can increase the possibility of type 1 errors, that is, accepting a false null hypothesis identifying significance in random patterns. Conversely, by tightening constraints too much, one could obtain the opposite result, by rejecting a true null hypothesis and failing to detect a significant non-random pattern. A typical situation in ecological analysis where those issues are much relevant is the analysis of binary matrices. These are commonly used to represent species interactions or the distribution of species across localities. In both cases, there are many interesting structural patterns that one can analyze. One of those is species co-occurrence, which quantifies species' tendency to be found together in the same locality. One classical way to assess co-occurrence is to identify subpatterns in the matrix where species A occurs in locality 1 but not in locality 2, and species B occurs in locality 2 but not in locality 1. A highly debated idea in ecology, which goes beyond this video scope, is that the abundance of similar situations might indicate an important role of competition in shaping the distribution of species across localities. Another interesting ecological pattern, which has received much attention in different contexts, including ecological network analysis, is nestedness. In a biogeographical metacommunity context, nestedness indicates the tendency for the assemblage of species inhabiting a given locality, for example an island in an archipelago, to be a subset of all more diverse species assemblages. If we look at this pattern from a matrix perspective, we have nestedness when, after sorting rows and columns according to the marginal totals, we can draw a diagonal in the matrix which separates most presences from most absences. It has been suggested that this pattern could be important to determine extinction risk at the metacommunity level, while in the context of ecological networks it has been proposed that nestedness, the tendency of sharing interacting partners, might be key to the stability of mutualistic systems. Thus, both co-occurrence and nestedness can indicate interesting ecological processes. However, both patterns are strongly affected by matrix properties. For example, with increasing matrix size and fill, that is the percentage of occupied cells, nestedness is expected to increase as a plain consequence of matrix structure, even if the presences are allocated in the matrix completely at random. As in the example of the dog bowl, generating a set of randomized versions of the initial matrix and comparing the nestedness measured there with that of the original matrix appear as a valid solution. But as in the example of the bowl, we need to define a proper set of rules for the randomization process permitting to discriminate structure from randomness confidently. It is intuitive that the random matrices need to be of the same size and shape as the initial one. It is also intuitive that they need to contain the same number of zeros and ones of the initial matrix. However, it has been shown that randomization based on these constraints alone produces matrices that are less structured than most real-world matrices. For this, the procedure tends to identify significant patterns even when those patterns are very weak, being therefore prone to type 1 errors. This calls for additional constraints, but what kind of constraints can we apply to a binary matrix? The most obvious ones are marginal totals. So we might generate random matrices that have identical marginal totals for both rows and columns to those of the initial matrix. If we think of an archipelago, controlling for marginal totals has ecological meaning. In fact, row totals represent the total number of islands where one species is found, and column totals represent the total number of species that are found in a given island. The total number of islands where a species occurs, that is, species prevalence, can be a result of the species dispersal ability and its ecological generalism. While the number of species per island can be a result, for example, of the island area or resource habitat availability. It might therefore be a good idea to control for this aspect in order to evaluate co-occurrence or nestedness patterns emerging from processes different from those affecting local species richness and species prevalence. However, constraining the marginal totals can produce the opposite result, that is, it might lead to failure in detecting significant patterns. This is due to the fact that the matrices created using the constraints will be very similar to the starting one, with this being particularly true for highly nested matrices. Paradoxically, if we take a perfectly nested matrix, there is no alternative random version of the matrix having the same marginal totals but different configuration. So, randomizing this matrix constraining the marginal totals will produce a set of matrices identical and with the same nestedness of the initial one, leading to the wrong conclusion that the very high structure of the target matrix is fully explained by our null model and hence not interesting. As a possible solution to this issue, at least applied to binary matrices, Nick Gotelli, Werner Ulrich and I propose an alternative approach where instead of basing conclusions on a single null model, one can compare the starting matrix with many different sets of null matrices built with increasing constraints in the marginal total match between the initial and the final matrix. In this way, instead of having a single potentially biased value of significance or effect size, one could have a bidimensional landscape of significance, revealing under which combination of marginal total constraints a structural pattern emerges. This, however, is more a workaround than a definitive solution, but perhaps a solution does not exist. Or does it?
Remember, all I'm offering is the truth, nothing more.